We are starting a new chapter today. 16.1, we talk about vector fields.
What do you see in these two pictures over here? What are the two pictures about? Both of them are indicating the wind speed at the Bay Area. You see those arrows there indicate the direction of the wind, and the length of the arrow here indicate the speed of the wind. So right here, we see that the air velocity vector. So those arrows here indicate the air velocity vector
at points 10 meters above the surface elevation.
Now we see that over here, the largest arrow is the one that I actually circle over here. This one over here is actually, this one here indicates the greatest wind speed because this arrow here is the longest among all this, which is going to happen as the wind enters the bay across the Golden Gate Bridge.
Now the second picture here is the wind patterns of this same area but at a different time. This one is at 6 p.m. and this is at 6 a.m. They are examples of velocity vector field.
At this time, the vector field here is velocity vector of the wind. So it is a two-dimensional vector field, right? On the plane, and the vector will be two-dimensional. So here's one example of a vector field. So every point in the air, we can imagine a wind velocity vector. So it's a velocity vector field on R2. Now here are more examples of velocity vector field. And this one here is the ocean current. So you see those arrows right here indicate the ocean current. So it's an example of a velocity vector field. This one here is more familiar. It's the airflow past an inclined airfoil. So this is the cross section of the airplane wing, right? So the airflow is past this. And you see the arrow here indicate the direction, and the magnitude that indicate the speed.
What's the airfoil?
An airfoil is a structure with curved surfaces designed to give the most favorable ratio of lift to drag in flight. An airfoil shaded surface, such as an airplane wing, produce lift and drag when moved through the air.
So this is the cross section of the wing of the airplane. Now, the one that we had just talked about, those are the vector fields on R2. Okay, so is on the XY plane. Now we also have vector field on R3. One example of a vector field on R3, three-dimensional, is going to be the gravitational force field. So here, think about this as the Earth. Then is every object in the space is going to be attracted by the Earth over here, and it's pointing inward, right? The gravitational force field pointing inward. The closer to the center of the Earth, the bigger the force field, right? If the mass of the object stays the same, the closer to the distance to the Earth, then the stronger the force, right? Okay. So you see the arrow is longer and closer to the Earth, and then it's further away and the arrow is smaller. So this is three-dimensional vector field, and it's a vector field on R3. So the domain of a vector field, so what's the domain of a vector field? The domain of vector field could be a set of points in R2. Let's write down. For example, what we had before was remember this one right here. The domain for the vector field is actually every point on this square over here, right? And what is the range for that one? The range of that is a set of vectors in V2. What's the difference between R2 and V2? R2 is every member in R2 is a point. Now what about V2? Every member in V2 is a vector. Okay? So the vector will look like this, and then the point here will look like parenthesis here for the point and angle bracket here for the vector. Okay? So it maps a point in R2 to a vector in V2. So go back to this, you see that for every point on the square here, it assigns a vector, right? And the vector here is a two-dimensional vector. Okay? Every point has an arrow associated with that point. And the example we have just done here above here, the domain here is a set of points in R3. So it doesn't have to be just in R2. It could be in R3. So it could be in R3. Then what will be the range of that? So looking at this, think about this gravitational force field. So under this vector field, every point in the space is going to map to what? A vector in what? V3, right? So in V3, a three-dimensional vector, right? Right. So, okay, now, so what is a vector field? Now think about, it is a function, right? We know function. We are familiar with function, right? At that time, we use the small f. But for vector field, we're going to use this big F notation with an arrow above it. So a vector field is a function that maps every point in R2 here to a vector in V2. And if this here is a point in R3, it maps to a vector in V3. So it's a function. The vector field is a function. So here is a formal definition. So here say, let E be a set in R2, which is a plane region. Think about like this one. A vector field on this R2 is a function indicated by the big F with an arrow on top that assigned to each point x comma y in this domain, in this domain over here, a two-dimensional vector f of x comma y. It maps every point x comma y to a two-dimensional vector f of x comma y, which is like that. Question. So this is it's a vector field on R2, right? So we can also have vector field on R3. So here is the picture. This, for example, the gravitational force field, right? So take every point in space. So it has x, y, z, this point. And then it's going to map that point to a vector, a three-dimensional vector, this one. So it has three components, this vector right here, right? Okay. The best way to picture a vector field is to draw an arrow, like that, representing the vector starting at the point x comma y. So you have this point x comma y, and then to picture the vector field, you're going to pick the point over here in the domain, and then you're going to start drawing arrow. And so you draw arrow right there. Of course, it's impossible to do this for all points, right? You cannot do for every point in the domain. Okay, there are infinite many points. But by just picking some points here, we can gain a reasonable understanding of this vector field by just picking some representative points, right? Okay, so the more you draw, the best picture you get, but just picking some points here and give you some idea of the vector field. Okay, now since the vector field is a two-dimension, remember it maps a point in R2 to a vector in R2, right? So this one here indicates a two-dimensional vector. So think about that. This is a vector. Okay, it's a two-dimensional vector. We can write it in terms of its component function P and Q. So you have two components. One is along the I direction, the other one along the J direction. So along the I direction, we have this function P of x, y,
and then along the j direction, q of xy.
This vector field is equal to pi plus qj. Notice that the p and q over here, they are scalar functions, right? The f here is a vector function. The output is a vector. The p and q over here, they are scalar functions. The output will be real numbers, right? So we call p and q here scalar fields to distinguish them from vector fields. So this is a vector field, and then the p and q over here called scalar field. Now this definition here is just extend the definition to R3. Okay? So here it says that if you have a set in R3, a vector field on R3 is a function that assigned to each point xyz in R3 in the domain of the function a three-dimensional vector f of xyz. So this one here is a three-dimensional vector. So R3 mapped to V3. Question. And then here's a picture of a vector field on R3, right? We just went over. So every point over here in R3, we associate that with a three-dimensional vector. The output of the function will be three-dimensional vectors. We can express this vector field over here in terms of its component function p, q, and r. So now it has three components, I, j, and k, and then it has those scalar function right here, right? P, q, and r. Actually, you can call it scalar field. Okay? Scalar field over here, p, q, and r. Scalar function, scalar field. You can call it either way. Okay, so well, when we talk about function, right? We normally think about the continuity, right? Is the function continuous, right? Now we have vector function. We think about how do we define the continuity of vector field. Okay? Vector function, vector field. I think they are interchangeable. And how can I show that this vector field, okay, this vector field F is continuous? Well, the vector field F here is continuous if and only if its component function P, Q, and R are continuous, which makes sense, right? If each component function here is continuous, then the vector field will be continuous. Now, sometimes we identify a point xyz with its position vector. Okay, so this point over here identify with this position vector. Okay. So x put a bar on top will be this position vector associated with this point, right? Okay. So if I identify this point with the position vector like this one, then the vector field, okay, or we say the vector function acting on this x over here, we can write it this way. Okay, so the vector function acting on this position vector x bar. Instead of writing this way, so these two are actually interchangeable. So you can either write it this way or this way. But this one here looks simpler that way. If you write it that way, then this f here become a function that assign a vector to this vector. Okay, it's better that we have some example. Let's look at the first example. This one here is a vector field on R2, okay, on the xy plane. And we define this vector field here by this formula. F here is equal to this. Here they ask you to describe this vector field by sketching some of the vector right here. I already gave out the answer over here. We sketch out right here. But you might wonder, how do we get this? How do we sketch this out? Any idea? You can just make a table and put in the x and y, right? And then you will get the vector. For example, I can make a table, and then I have the vector. Think about the point here is 1, 0. what will be the vector? Okay, if this input this into this vector field, what will be the output? Yeah, 1j, right? So you're going to get negative y. Y here is 0, right? So that is going to be 1j. So just j. Okay. So the output over here will be this vector j. So at 1, 0, so let's think about maybe over here. Wait, 1, 0 is this one. 1, 0. Okay. And then we're going to associate this vector j, right? Okay. J is a vector pointing upward, right? That's it, right? That's the j vector. Okay. So you will have a vector here associated with this point. Okay. That's the output of this vector field at this point. Okay. Right. I want you guys also to do this one. What about the one? What will be the output? Negative I. Yes, you got negative I. The output will be negative I. So the one, put it over here, and then it's negative I. So it will be pointing to the left, right? Yeah, you got it. So you have this, right? Okay. Now continue this way, so we can make a table. Now here's the table. Okay. So we make the table over here. So plug in the point, and we got two-dimensional vector associated with each point. Then what do we see over here is it's going to be we draw the vector, right? Some of the vector, and we see the vector field. We can get some feeling of the vector field. It looks like this. So what do you see? Well, from this picture here, we kind of suspect that each arrow. Look at the arrow. It's kind of tangent to a circle, right? Tangent to a circle with center at the origin. So it looks like the arrow here is going to be, each arrow is tangent to a circle with the center at this origin. But how can I confirm this? Yeah, you take the dot product, right? So you can take the dot product. So here is the vector field over here. This is the vector field. And then for the circle over here, this point, we want to see that this is going to tangent to the circle, which means that it's going to tangent to the vector. Now think about the position vector of this one, which is this one, right? And then like this one here is the position vector of that one. And then position vector of that, position vector of that. And that is the position vector x bar, right? Okay. Now if I can show that the x bar and this vector over here, that associated with this point, if they are orthogonal, then I show that this is going to tangent to this circle, right? Okay. So to do this, we take the dot product. Okay. So we're going to take the dot product of the position vector. Okay. This position vector over here. And then with this vector, the blue one, this is the blue one over there. Let's take the dot product. Okay. So I have x bar started with equal to. Well, I'm going to put this notation. X bar here is, it has x and y in here. And then dotted with, what should I put as the first component for this one? F negative y. Yeah, so that's negative y. Okay. This one, negative y. And then this one here is x. Take the dot product. And that's equal to negative xy plus xy. So that's equal to 0. So the dot product of these two equals 0. So what does it mean? That means this position vector and this vector here associated with this one, they are orthogonal, right? So when they're orthogonal, then it's always orthogonal, so it's going to be tangent to this circle. Okay, so this vector field, okay, each vector is perpendicular to the position vector. Okay, so therefore it's going to be tangent to a circle with center at the origin, and the radius of that. What's the radius for the circle? The radius for the circle will be the magnitude, right? The magnitude of this position vector. Okay. Yeah. The magnitude of the position vector, which is square root of x squared plus y squared. Okay. So here, actually, we get more vector. If you draw more, and you get a better picture, and you see the vector field. Each vector is going to be tangent to a circle with center at the origin. Okay. It looks like a tornado. yeah, tornado. Okay. Okay. Yeah, and also when it's actually closer to the center, right, closer to the origin, the magnitude looks smaller, right? And then the further away, the magnitude gets bigger. So here and then bigger and bigger, right? Okay, tornado. Yeah, that's a good expression. I like that one. I'm gonna make a video, put a tornado in there. Okay. Notice also that the magnitude of this vector that associated with that point, right, is going to be, if you do the calculation, that turn out to be the same magnitude as the magnitude of the position vector. Right? Did you guys have a good time? Great. So that's the first example. We draw a vector field according to the formula, right? So we make a table and we start plugging the point in to get the vector, and the more vector we get, the better picture we can get about the vector field. So this looks like a tornado, you said. Okay, great. Okay, now I want you to try the second example. Try this second example to sketch the vector field on R3. Notice that the input of the vector field here is a point in R3. So the output will be a vector in V3. Can you guys think about how does it look like? It looks like the formula here is relatively simple, right? So this vector field has a simple formula. So let's draw the coordinate axis. So given by this. So this vector field given by this, let's write this in this way. So the x component will be the along the I direction will be what? It's going to be 0, right? And then j component here was 0, and then the k component here will be z, right? Will be z, okay? So it will be z right here because this is z. So we have that. Now we can start plugging forth. Okay, that's simple. This is plugging. What about at the center? What will be the vector associated with that? Will be 0, 0, 0, right? The vector will be the 0, right? The 0 vector. Okay. And then let's say, well, you see this vector here actually just depends on the z, right? The x and y is not going to affect the vector, okay? So depends on the z. So if z over here is 1, then how does the vector here look like? it's going to, at this point, and it's going to point upward 1 unit, right? 1 unit over here. Okay. Is this a plan? Let's draw more and then you will get an idea, okay? So what about another point that has z coordinate to be 1? Do they have the same vector? Right? It's the same vector, 1. So as long as d is equal to 1, yeah. Oh, you're right. So on the plane d equal to 1, okay, so let's draw the plane d equal to 1. Then all the vector will be like this, right? It's going to be point upward and has magnitude to be 1, right? Then what about if you have a plane that has z equal to 2? The vector will look like, how does it look like? It's going to point upward 2 units, right? Okay. Yeah. The magnitude is equal to the z component of the point. Okay. So since all of this point has the z component to be 2, then the magnitude will be 2. Right? And similarly, what about at the plane that z equal to, say, down here, say z equal to negative 1. Yeah, it's going to point, so it's going to point downward like this. So you see the idea, right? You got the idea. So for every horizontal plane, they had the same vector, right? And depends on the d. So we're able to draw this vector field in this example by hand because this particular simple formula right here, right? Most three-dimensional vector field, however, are virtually impossible to sketch. Okay, to sketch by hand, okay, is very difficult. So we need to use computer software to draw those vector fields. Okay, for simple one we can draw like this, but for complicated one we use computer software to do it. Okay, do you guys want to try one more example to draw a vector field? Okay, now let's look to the practice problem down here. Try the first practice problem. Sketch the vector field by drawing a diagram. This is the formula for the vector field. Could you guys try this? So this is a two-dimensional, the domain for that is on R2, right? So the output will be on V2, okay? So let's draw think about it. Okay, did you do it? Okay. How about we do it together? Let's rewrite this in this way, right? So the x component is 0.4 and the y component is negative 0.3, right? Okay. So this is a constant. It's a constant vector, isn't it? It's a constant vector. So which means that it doesn't depend on the location of the point. They always have this constant vector, right? So how does it look like? Well, so along the x direction, you're going to go 0.4, right? So you go 0.4, okay. And then along the y direction, you're going to go down 0.3. So it's going to look this way, right? So the vector is going to look like this. So for every point over here, you're going to have this vector here. Okay, so I'm going to actually draw the same vector here. I'm going to copy this and then I'll paste it. So for every point on the domain, in this case actually it's all up to the vector, the output will be the same. It's a constant vector. So like that. All right. So this one here is very simple. It's a constant vector, right? So you have that one. Okay. Now, what about, want to try another one? Question for this one? So the next one over here, can you match this vector field with the correct plot? Which one? It's a multiple choice. Which one you think is going to be? And can you give a reason? You say D?
Yeah.
Okay. Andrew, yes. Can you give me some reason?
If you're looking at the first one where they're both positive, it's the only one that's pointing down to the right.
Yeah. You're right. Very good. So it depends on the quadrant, right? So we can start. So okay, let me draw this. So we have, so this is X and Y. Look at the first quadrant, right? So if you look at the first quadrant, then the X is positive, right? So look at the vector. X is positive. So X is positive. So you have positive for this first component, right? And then Y is positive, so you have negative for the second component, right? Okay, because X and Y are both positive. So X component here will be positive, so Y component will be negative on this, right? Okay, let's look at the second one, the second quadrant. So what will be the sign for the first component, second component for the vector? X is negative, right? Okay, and then the Y is positive, so it will be negative. Okay, so it's negative. Okay. And then this one over here, you have X is negative, so negative, right?
Yeah.
And then the second component here will be what? Positive. Okay. And then finally, this one is positive, right?
Yeah.
And then what? Positive. Okay, let's see. Which one match you think? So let's look at this one. This is positive, negative. So what kind of vector do we have? It looks like the vector positive X and then negative Y. So it's going to go this way, right? This way, right?
Yeah.
Okay, and then, and then for this one, negative is going to go this way, right? And then this one here, negative, positive, this way, right? And then positive, this way. So the first quadrant, it looked like this. So definitely, this one. So the only one that matched this is going to be this one, right? If this one here is the Y one. Because you see here, it goes this way, and here goes this way, and here goes this way, and then here goes this way. So that's the one that match, right? Okay, good job. Okay, all right. Let's try another one. This one.
Could you match the vector field with the correct plot?
Hey, you're very good at this. Why? Why is it A?
Yeah, the constant B coordinate and then have a 4.
Very good job. Okay. So, and you say that because the K component over here has a constant, right? 4. So the vector, the output here is going to be X, Y, and then it stay at 4, right? Okay. So it's constant. So we can actually rule out some of them.
B and D.
Which one?
B and D will roll out.
B and D. Okay. Oh, let me put A, B, C, D. A, B, C, D. Okay, let's see. So because this D component here is positive 4, right? Positive. So when it's positive, that means it has to point upward, right?
Yeah.
So it's going to point upward instead of downward. So if you see any one of them has arrow pointing downward, then you can eliminate them, right? So now this one here has pointing downward, right? So not this one. And this one over here, upward. This one here pointing downward. So these two we can eliminate, right? They have arrow pointing downward, okay? And what else can we do?
If you plug in an X negative to the X value or negative to the Y, you will go.
Yeah, okay, very good. So you can try to plug in some point, right? So X and Y.
Hold on, you can eliminate it right now. If you plug in 0 for X and 0 for Y, you should have stuff pointing straight up the middle. And the only one that has that is X.
Very good, very good. So let's think about it. Okay. So Andrew has the idea. Okay. You plug in. Say that one more time.
If you plug in 0 for X and 0 for Y, you should have vector field pointing straight up the middle. Right?
Good. So he start plugging the point X. So the point here will be the point was 0, 0, right? And then whatever here. Okay. So when X equals 0, Y equals 0, then what happens is the output is going to be 0, 0, 4, right? So when X and Y equals 0, so that will be in the X equals Y equals 0 here. X equals 0 is Y. Okay, X and Y equals 0. So it will be all those points. This point right here, X and Y equals 0. Think about that. You have this right here or right here. So X and Y equals 0. Or along the z-axis, right? Along the z-axis. So along the z-axis, the vector is going to be 0, 0, 4. Okay, you said that, right? It's going to be 0, 0, 4. So it's going to point upward 4 units. So it's going to go upward. So go upward 4 units. Now looking at this, okay, so we have either this one or this one. This one here doesn't, right? Yeah, it's not pointing upward. So this one here, it doesn't point upward along the z-axis. So it's not straight upward, right? It has to be straight up 4 units. So it's only this one. So this is the one. So A is right. Okay, all right. That's very good. Okay, very good observation. Good job. Okay, all right. Now let's go back. Now look at this example over here. Okay, so we imagine a fluid floating steadily along a pipe and let V, XYZ be the velocity vector at this point XYZ. V assign a vector to each point XYZ in a certain domain E, which is the interior of the pipe. And so V is a vector field on R3 called a velocity field. So you look at this picture over here. Okay, so this is a possible velocity field illustrated over here. Okay, so let's try to think about what's this. So you have a point. So you have a point over here. It's XYZ. Okay. Every point right here, XYZ, like that. And you're going to associate a velocity vector. So each point has this velocity vector, the blue arrow there. Okay, right. And then the speed at any given point is indicated by the length of the arrow. Okay, and what do you observe here? Looks like along the middle is the constant speed. Okay, the length of the arrow is the same. And then over here, it goes along the inside of the pipe, right? Okay, so describing the counterclockwise direction, velocity also occurs in other areas of physics. Did you guys notice did you guys learn about this in physics? The velocity field in physics, right? So remember in example 1, we have this velocity field like this, right? And this is another one, okay? So these two are velocity fields. Okay, so this one here can be used as a velocity field also, describing the counterclockwise rotation of a wheel. Okay, so when you rotate the wheel counterclockwise, then this one here can describe the velocity field. Okay, all right. Okay, there's some physics here today. Do you guys remember Newton's law of gravitation, right? Yeah, you remember. That's good. What does it say? It says that the magnitude of the gravitational force between two objects, like think about this object and this object, like the Earth and the Moon, right? The mass for the Earth, let's call it the big M. The mass for the Moon, let's call it small m. Then the magnitude of the gravitational force between the two objects is given by this formula. So is the mass of this object times the mass of this object, and then times g, and then divide by the square of the distance between them. And what is this g? G here is, the universal gravitational constant, which is given by this number, okay?
They have the same for calculating the magnitude of charge. It's the same equation, but g is a different constant. And the two masses of the charge is multiplied.
You are ahead of me. We're going to get to that the next stage, but you're very good at it. You remember, okay?
No, that was the easy part. You didn't put it on the test. It was easy.
That was an easy part. Okay, all right. Okay, good. So that's Newton's law of gravitation. So the magnitude of the gravitational force between the two objects is the product of the mass of the two objects times this constant, which is the universal gravitational constant, divided by the square of the distance between them, right? Okay, good. All right. Sometimes you put the G here in front and put it this way.
So there was like a meme, right? Where Newton had made that, and then the other guy was looking at his paper, writing it down, and he was like stealing that from him to make the other one. It's like a meme. It was funny though.
Oh, could you send it in a Ponto or in a discussion? Send me the meme. Okay, I'll allow to see it. Okay, great. Okay, let's learn some physics today. So we let the position vector of the object with mass m. Okay, so suppose this one here has mass big M, and think about that. This is in the center at the origin, right? And let the position vector of the object with small mass m, okay, small m, okay, and let this here to be the position vector of a point. So think about this is the Earth. Okay, think about you have an object, outer space, okay, and has this XYZ, okay, has this XYZ coordinate, okay. So the position vector of this point in outer space will be X arrow right here, which is the position vector of this point, right? Then the R here from this object to the center of Earth. Okay, think about that. The other object here is the Earth. Is the R. Okay, it's the R here. R here is from the object to the center Earth. So R square will be the square of this. Then the gravitational force that is acting on the second object over here toward the center of the Earth, and so the gravitational force will be from here and pointing to the center of the Earth. Okay. Well, what's the unit vector in this direction? The unit vector in this direction is going to be, you take this position vector, right? And then divide by the magnitude of the position vector. And why is that negative? I think it's because it's pointing this way to the center of the Earth. So it has a negative sign here because of gravity, right?
Therefore, the gravitational force acting on the object at this position vector x is given by this formula 3.
And physics often use this notation R instead of this x over here. And this is a formula. Okay, replace that. So we have this formula. So this function given by this equation is an example of a vector field. It's called the gravitational field. All right. Okay. What's the magnitude of this x here? It's the magnitude of the position vector, right? So it takes the square root of x squared plus y squared plus z squared. So this vector field can be represented this way. Okay. So you break it into the I, J, and K component like this. So each one of these is a scalar field, and then this vector field is equal to this. Okay, so basically this one here is just break it down into the 3 components. Okay, and then here's the picture. The closer to the center, okay, the bigger the magnitude. If the mass stay the same, then bigger the magnitude, right? All right, so this is the gravitational force field. Okay, let's look at example 5. Yeah, this is what you talk about, Angel, right? So now we're going to talk about electric charge. Okay, Q. Okay, so think about them. You have this Q. So you have the electric charge Q over here, and then you have another one. This. Then there will be force, okay, between these two, between this Q and this Q. Okay, so let's put this big Q here at the origin. Okay, according to
Coulomb's law. Coulomb's law.
Coulomb's law. Oh, he's copying Newton.
Yeah, he was going like this.
He's looking like this, looking at Newton's work, and he copied Newton, and they come up with this formula. Actually, this reminds you of the gravitational vector field, right? Except this time, this replace the mass, the big M by big Q, and the small m by small q. And this sigma over here, instead of the gravitational constant, is this sigma. Sigma is a constant, depends on the unit used. So I put the two formulas together. This one and this one. This one by Newton, right? And this one by what? Coulomb. Okay, so both vector field are example of force field. Okay, that's the force between them. Those are force fields. All right, and instead of considering the electric force F, this is often considered the force per unit charge. How do you get the force per unit charge? You take the force over here, right? And then divide by the charge, right? So divide by the charge, you get the force per unit charge. Okay. So when you divide by Q, then this Q here divide out, and then you will get this one here. And this E here is a vector field on R3 called the electric field. Next one, we're going to talk about gradient field. If F here is a scalar function of two variables, so its gradient, remember this one here, it's called del F. Okay, it's called del F, or you call gradient of F. How do you define gradient? Do you guys remember? You take the partial derivative, right? Take the partial derivative of each component function, right? And then this will be the gradient, right? So the gradient of F here, if F is a function of two variables, the gradient F is a vector field on R2 because it takes a point in R2 to a vector in V2, right? You have two components, this vector. And it's called a gradient vector field. Okay? And if the small f here is a scalar function of three variables, then the gradient will be a vector field. It's a vector field in V3, right? So it has three components right here. Okay. The gradient of a scalar function in two variables is a vector field in V2. And the gradient of a scalar function in three variables is a vector field in V3, right? All right, now let's look at example. Can you find the gradient vector field of this? This function here is a scalar function in how many variables? Two variables. Then the gradient vector field will be in V2, right? Okay, so all right, let's find the gradient vector field. How do you find this?
It's the part that you said, right? It's like those vector fields are like the electric field, and those other lines are like the potential, something like that.
Okay.
And like a grade, they're like perpendicular.
Okay, I see. Okay, let's try this together. Okay, so how do you get the gradient vector field? You take the partial derivative of that scalar function, right? So let's take the partial derivative of this scalar function first with respect to x, and that will give you the I component, right? And then you take the partial derivative of this scalar function with respect to y, that will give you the j component, right? Can you tell me what's the partial derivative of this function with respect to x? You got it, 2xy, and then that is the I component, right? And then you add. What's the partial derivative of this function with respect to y? X squared minus 3y squared. And then that will be the j component, right? Okay. So this is a two-dimensional vector, right? Okay. This is the gradient vector field of the scalar function f. And then over here, here's a picture, okay? Here's a picture. It's a contour map of this scalar function with the gradient vector field. So you see the pink, which one? Okay, the pink one is actually the graph for this small f. Okay, so the pink line here, those are the graph for the scalar function. The blue arrow, those are the vector, two-dimensional vectors. Okay, each blue arrow here is a two-dimensional vector, is a vector in the gradient vector field. And what do you see over here? The further away from 0 is bigger, right? So when x and y increase, actually when x increase, okay, then it's going to, you see the arrow here? It's different, right? At 0, 0, what will be the vector, the gradient vector at 0, 0? Substitute x and y to be 0, you get what? You get 0. You get a 0 vector right here, right? Okay. So, and then also, what do you notice that the gradient vector, you see the blue arrow, they are orthogonal to, the level curve. The pink one here are the level curve of this scalar function. Those are the level curve for this scalar function. And then the gradient vector, look at the blue one, it is perpendicular to the level curve, right? So form a 90-degree angle with the level curve right here. Okay. What else we want to see? The gradient vector are long when the level curve are close to each other. You see right here, the level curve are close to each other, and then the gradient vector is long. And then short when the curve are further apart. So here and here is further apart than like this. Okay. What's the reason? Looking at this formula for the vector field. Okay. The length of this gradient vector. How do you find the length of this gradient vector? Can you tell me? You take the square root of what? The square of this plus the square of this, right? Then you see the gradient vector. The length of the gradient vector is the value of the directional derivative of f, and closely spaced level curve indicate a steep graph. Oh, yes. So, yeah, remember the directional derivative of f? The magnitude of that is the length of the gradient vector. Okay, so we're actually done with this section. This one. Okay, would you like to try some example? Okay, let's try number 4. Can you guys try number 4? This one has a lot of things. Okay, let's try to do it together. So I'm going to ask you, what's the magnitude of this vector? Can you guys tell me? To find the magnitude of this vector, we will square each component, right? And then sum them up and take the square root, right? So when I try to find the magnitude of this, I'm going to take this 1 over square the x square over y square out. Okay, so I can put it this way. 1 over square the x square plus y square. And then here will be the y and here's the x, right? Like this. So when I try to find the magnitude, I will have this 1 over square root of x square plus y square. And then I will take the square root, right? Take the square root of what? Y square plus x square, right? Now, simplifying over here, what do you get? You get 1. Yeah, you get 1. So which means that the vector, each one of them, doesn't matter which point you are at, the magnitude is always 1, right? It's always 1. Okay? So it's always 1. So when I draw this is on R2. So it's always 1. Let's try to practice some form, okay? Maybe we can go along. Let's think about along this x-axis. Okay, let's think about along the x-axis. Along the x-axis, we'll have y equal to 0, right? Say along x-axis, then we're going to have y to be 0. Then what happened here to the vector? So what will be f of x comma y? F of x comma y will be equal to f of x comma 0, right? Like that. So y will be 0, okay? So that will be equal to, according to this formula over here, that will be, we know the magnitude is 1, so it's going to be 1 over, we know the magnitude is 1, we just need the direction, right? So 1 over square root of x square, which is 1 over x. Okay. And then what do I have here? Yeah, did you just say so? So for the first component, and then the second component will be what? This one here is just 1 over x, right? 1 over x. So simplifying here, this is what? It's going to be 0, 1, right? So along the x-axis, all the vector will be 0, 1. How does 0, 1 vector look like? It's going to be, it doesn't go left and right, and only go what? Up, like this, right? So this is the J vector, right? This one. So we are going to have this. So along the x-axis, it's going to be like this all the time, right? Wait. Oh, when x is positive. When x is negative, oh, there's something here. This is when x is positive, right? Because 1 over square root of x squared here, basically should be the absolute value of x, remember, right? So when x is positive, this is when x is positive, it's going to be 0, 1. What happens when x is negative? 0, negative 1. When x is negative, yes, you got it. So when x is positive, it will be the J vector, but when x is negative, it actually goes down like this. It's a negative J vector. Negative J vector right here. Okay. All right. Now let's think about along the y-axis. Okay. Let's think about along the y-axis. What happens? So x will be 0, right? And y. So the vector is 1 over the absolute value of y times y here, this y, and x will be 0, right? X will be 0. So looking at this, when y is positive, what do you get? Positive 1, right? So when y is greater than 0, this one here is going to be this 1, 0. So you're going to have the vector pointing to the right side, right? So it's going to go this way, right? So this way, 1, 1, 1. When y is negative, what happens when y is negative? Y less than 0, then you have negative 1, 0, right? They go this way, point to the left, right? Okay. And then what happens when, and then you can also try to do along this, you can also try to do along this line here, y equal to x, okay? And along y equal to negative x. And you can try to plug in the value over here, calculating, okay? Then you see that, what happens when y equal to x? Can you tell me when y equal to x? At the first quadrant, what do you get? When y equal to x, this one here will be 1. Okay, so you can try that. When y equal to x, along this direction, when y and x are positive, did you say 1/2? Let's try this. So it's 1 over, let's just replace by x. So that will be square root of, say, 2x squared, and then y equal to x. So that will be this x comma x. This one here is going to be, put it down here. So that is 1 over square root of 2. And that will be x over the absolute value of x over the absolute value of x, right? So when x is positive, this is going to be 1, 1, but times what? 1 over square root of 2, right? Okay. So you're going to have the arrow here will look like this. 1, 1. So it's going to be like this. It's going to point this way. When it is negative, then it goes the other way, like this and this. Okay. And you also can do for y equal negative x, and you will also see something like this. Okay. So we kind of see the vector field like this to draw it. Okay. I guess this one here will be multiple choice. Okay. You can see that one. Okay. All right. Let's try the last one over here. Can you find the gradient vector field of this f? How do you find the gradient vector field of a small f? You take the partial derivative, right? Okay. Okay, you guys try first. So the first component, take the partial derivative with respect to x. What's the partial derivative of this function with respect to x? Remember, you hold the x here, think about as the only variable, and hold y and z as constant, right? So you get what? 3x over square root of x squared plus y squared plus z squared, right? Okay, good. Similarly, what will be the partial derivative with respect to y? Okay, good. And then partial derivative this with respect to z? Yes, you got it. Okay, good job. So the gradient vector field here, you just take the partial derivative with respect to x and y and z correspondingly in each component. And that's the gradient vector field, right? All right, so that's all for today.